Okay, in this video we're going to be talking about something that we haven't really discussed yet, and that is the idea of molecular structure determination. We've looked at a whole bunch of reactions and naming conventions for molecules with different functional groups so far, but the one thing we've never really looked at is how to actually tell what you have, or if you think what you have. We've used melting point before. We've used this in lab a bunch of times. We've also done a little bit of TLC, but it turns out there are much more involved techniques of telling not only what you have when you run a reaction, or if it's what you think you want it to get. And the first two techniques that we're going to look at are those called mass spectrometry. You'll see this sometimes on shows like CSI, where you see the scientist who's always wearing the white lab coat, who uses something called a GCMS. MS here is MS as in mass spectrometry. It's an identification tool. And then the other method that we'll use is infrared spectroscopy. And each of these two does different things, interacts with the sample in a different way. This method here is completely destructive to the sample, so the sample's gone after you've measured it. This IR is not destructive, so you can get your sample back after you're done. And they both tell you completely different things. That the main thing that mass spectrometry is used for is for determining the molecular weight of the molecule and some basics about its structure. Infrared spectroscopy, the main thing that this is useful for, this isn't really very useful for telling you what the general makeup of the molecule looks like, what its general structure is, but it does tell you some very useful stuff about different types of functional groups present in the molecule. So if you have maybe an alcohol, a carbonyl, a benzene ring, an amine maybe, or something else, infrared spectroscopy, or perhaps an alkene or alkyne. Infrared spectroscopy, nitrile as well, can be very useful for that, but it won't tell you much about the actual makeup, the actual structure of the molecule, unless you get really, really good at it. So let's concentrate a little bit on mass spectrometry first. Very simply put, when you have your mass spectrometer, what it does is it hits your sample with a whole beam of electrons, all right? A beam of high energy electrons. So let's say you have a sample here of, I don't know, let's say we have Penta. What this thing does is it sends in a massive amount of electrons and literally like a laser, and hits them with this, and hits this molecule with that bunch of electrons. And what happens is those electrons smash into here and actually cause one electron somewhere in the molecule, usually the highest energy part, to break off. And so what you get left with is a highly reactive species that's missing an electron. So it's a radical species because it's missing an electron. It's also a cationic species because it's got one electron less. Very, very unstable species, and so therefore doesn't last very long. And then what this does is this breaks down or fragments into smaller fragments. Might look something like this. Some fragments will have radicals, some fragments will have positive charges, and it's the positively charged fragments that get picked up in the magnets of the mass spectrometer, and depending on their size and charge, that tells you, or that identifies how fast or slow they'll actually go to the detector. So it's a mass to charge ratio thing. So the idea is that each different piece with a different size and a particular charge will hit the detector at a different time, and you'll get a very characteristic looking spectrum from a mass spectrometer. So this guy actually looks at these charged species here. And this species is called the molecular ion peak, and it usually has the node of M+. So the molecular ion peak. Okay. And because all you've done is lose an electron from here to here, this and this have the same molecular weight. This doesn't show up in the mass spectrum, this does, so it's a good way of telling you what the molecular weight of whatever you shot in there looks like, or whatever the molecular weight is. Anyway, let's take a look at an example. This is an example of a typical mass spectrum. And usually the M+ peak, the molecular ion peak, is the peak that's furthest to the right in the spectrum, because the scale increases in size here. This is a size to charge ratio, implying the charge is a charge +1. So as you get bigger, the sizes of your species get bigger. What this actually means here is the M+ peak here is actually this one. This is our molecular ion peak. And it actually occurs at this, the scale here isn't shown very well, but this has a mass to charge ratio of 98 units. Meaning the molecular weight of this sample was 98 AMU, 98 grams per mole. Now one thing you're probably wondering is, well, hang on a minute, that peak isn't furthest to the right in that spectrum. What about this tiny little one here? This one right here. I'm not blind, I can certainly see that that's there. Well, what this is due to, there's always going to be at least a peak that's either very small, or depending on what atoms are in there, of smaller size or similar size, next to the molecular ion peaks, just slightly bigger than it. This is due to the fact that this molecule only contains carbon and hydrogen. Alright, or perhaps it contains oxygen as well. And the fact is, carbon exists as 3 main isotopes, or really 2 main isotopes, really. That's carbon-12 and carbon-13. Now that carbon-12 is about, what is it? I think it's about 99% of the makeup of all carbon present. And this is about 1%. So naturally occurring in every single molecule, you're going to have a small peak that's one size bigger than your molecular ion peak, and this is called the M+1 peak, corresponding to the same molecule but that contains that isotopic carbon that's 1 unit bigger. So it doesn't mean the molecular ion peak is 99 here, it means the molecular ion peak is 98 and the tiny little peak next to it is just the M+1 peak. So that's one thing you can get from a mass spectrum. The other thing that you want to look out for is something called the base peak. Now, contrary to what the name might suggest, the base peak is the biggest peak in the spectrum, the one that has either 100% abundance or close to it, which in this case tops off right here. And this peak, if we were to have a ruler here and we could actually figure out what the scale was, let's see, we would see that the sample here was, hang on. So what we can see is that this guy here, the base peak, has a mass to charge ratio of 69 units. Now the reason why this is helpful is, first off, the base peak tells us that this fragment here corresponds to the most stable fragment that's come off from the parent ion. Most stable means there's a bunch of it, hence why it exists in a very high percentage. So if we can figure out what that corresponds to, we can figure out what actually came off from here to here, and this tells us, and this structure tells us something about what we've lost, or what was originally present in the molecule. So what we do is, well, let's see, 98 was the molecular ion peak. 69 was the mass to charge ratio of the base peak, so therefore that difference is 29. Now 29 AMUs what you can do here is you can figure out, well, what sort of group, usually some sort of alkyl group, what corresponds to something of size 29? Well, if carbon's 12, hydrogen is 1, then what you'll find out is that actually corresponds to CH2, CH3. 12, 24, 26, 29. Alright, so that means we lost an ethyl group going from here to here. In other words, there's an ethyl group somewhere in the molecule. And then, so the rest of it is whatever can be made up with a mass-to-charge ratio of 69. So this tells you something about the structure, and it's one of the things that can be useful about a mass spectrum. You wouldn't normally be expected to figure out the entire structure of something from the mass spectrum, but this sort of thing is a useful piece of information to start you off. So let's have a look at another one. This one is kind of similar. We have another molecular ion peak at the same size. And we have the n+1 peak again. When those two peaks are approximately in a ratio of 100 to 1, this is a little bit bigger than that, but that's basically it. May even be that this one's 98. Anyway, we look at we say, okay, well, our molecular ion peak is 98. And usually when you're given these things, the scale will be written in a much clearer detail so you can easily see what is going on. When we look at the base peak here, first off we see that it's here. Alright. And we see in this case the mass-to-charge ratio is, in this case it's 81, 82, 83. And if we just do the same thing again, 98. When we think 98 and 98 here, these two are probably isotopic in some way. 98 minus 83, now that gives us 15. So in this case, from our molecular ion peak, it fragmented to give a most stable fragment, having lost something of size 15. And again, carbon's 12, hydrogen's 1, so that corresponds to somewhere in that molecule there was a methyl group. Here you lost a methyl group, here you lost an ethyl group, so you can see that we have useful information that we can get from this mass spectrum. And basically, that's one of the useful things that you can get from using mass spectrometry. A couple of the other things, or a couple of the other useful things that you can get from it when you look at halogens. All right, let's use Cl and Br as two examples. All right, chlorine naturally exists as two main isotopes, chlorine 35 and chlorine 37. All right. Now, chlorine 35 has an isotopic ratio of 75% to approximately 25% to chlorine 37. And so what this means when you have a mass spectrum, okay, that's supposed to be a straight line, and this is your mass to charge ratio along the bottom. If you have a molecular ion peak at whatever weight it may be, whatever weight the molecule happens to be that contains chlorine, and then you have a peak 2 units away, so let's say this is X, and then a little bit later on we have X plus 2, whatever that is. We have another peak here that's in a ratio of approximately 3 to 1. So when you look at the size of these two, and you see the ratios are approximately 3 to 1, that's going to be a very good bet that in your molecule you have chlorine. Now bromine, on the other hand, has kind of a similar situation. It also exists as two main isotopes, but these guys, this is bromine 79 and bromine 81, but these two have an isotopic abundance of approximately 50-50. All right? So that means when you have a mass spectrum here. It's a little bit better. You have your mass to charge ratio along the bottom. If you have your molecular ion peak here as X, and then you have the same thing, you have your M+2 peak. So usually we see an M+1 peak, but when you have your halogen, you'll have an M+2 peak, or when you have chlorine or bromine. As these two have an isotopic ratio of 50-50, then that means the peak 2 units higher should be approximately the same size. And this is the kind of thing that you'll never see unless you have bromine present, because there aren't any other isotopes like this that are split 50-50. Notice the ratio of these is 1:1 if this is your molecular ion peak. And if that's the case, it's a very good bet that your molecule contains bromine. One of the very useful things that mass spec can do for you. Now, let's move on to our next technique here. And this is called infrared spectrometry. Now, what we actually have on this page is a set of characteristic absorptions of different functional groups. The idea in infrared spectroscopy is you have your oh boy, okay, that's supposed to be a sample vial that whatever sample is in it looks kind of crap. Let me try that again. No, that's just as bad, isn't it? Oh boy, that's even worse. Okay, so you have your sample, and you have infrared light of varying wavelengths that comes in here and goes out here. The intensity of the initial light is measured. The intensity of the light going out is measured, and these two are compared. If, for a particular wavelength, if your molecule has functional groups in that absorb some of that energy, the idea is that I0 is going to be considerably less than I initial because some of that energy has been absorbed by your molecule. And what happens in infrared when molecules are hit by infrared radiation? Let's just draw out an example of methane, for example. Infrared radiation is strong enough to make your molecules bend or stretch. So it can make this bond stretch, can make this bond go shorter, can make this bond wag left and right, kind of like the tail on a dog. So absorbing infrared energy is not enough to make a molecule's bonds break, but it's just enough to make them bend and stretch, okay, when they absorb that certain amount of radiation. So bending and stretching, these going back and forth, or this going left and right, these are molecular absorptions of energy and cause the energy going out of the molecule to be less than what came in. And so what happens is, here's a sample infrared spectrum. Transmittance is essentially the percentage of the light coming out versus the light that originally went in. And if you have close to 100% transmittance, as we do at this particular point, then that means that the amount of energy going in is approximately the same as the amount of energy coming out, therefore very, very little is being absorbed by the molecule. But if we compare to this region down here, where the transmittance is, somewhere down in the region of about, 4%, that means 96% of that energy going in is not coming back out. So it's being absorbed by the molecule. Because if you just measured infrared, the infrared spectrum of nothing, you would just see a straight line going all the way across here. But you introduce molecules and they interact with that energy and take the transmittance down. So the idea is you have a situation where your standard infrared spectrum shows you that at different wavelengths of infrared energy, which are represented from along this scale here, This scale represents the potential vibration of every single different type of bond around, whether it's double bond, triple bond, or a single bond. And they all absorb in different areas of the spectrum. You'll find that single bonds, whether that's CH, OH, NH, those tend to absorb around the 3,000, maybe about just below 3,000 wave numbers and above. So this is the kind of area for single bonds. And double bonds tend to absorb slightly lower down, and then triple bonds tend to be a little bit lower down too. So each of these little dips here, whether it's a really wide dip or a really sharp dip, corresponds to a particular type of energy absorption. Now, notice there's a little dip here, there's a bunch of little dips here, there's a couple of little dips there, there's this. I mean, there are all sorts of dips here. And so the one thing you want to be careful about with infrared spectroscopy is remembering that the last thing you want to do is to try to assign absolutely everything in an infrared spectrum. It's kind of pointless, and it's going to give you a big headache. In fact, usually for an infrared spectrum, you'll be concerned about the area from 4,000 to about 1,500 wave numbers. This is called the functional group region, and below that, from 1,500 down to 0, is known as the fingerprint region. Now, the reason this is called the fingerprint region is that every single molecule out of all the hundreds and thousands of molecules that are known have a different and distinct infrared characteristic fingerprint region. Does that mean you have to recognize every peak in the whole region? No, of course it doesn't. Hence why we're going to concentrate on the functional group region. However, there are certain peaks it's useful to know something about around the fingerprint region, usually those 1,500 to 1,000 wave numbers. Anyway, one of the things that we said before was that infrared is very useful for telling you something about functional groups in a molecule. The actual structure, the actual framework of the molecule, the actual carbon skeleton, this is not very useful for. Like I said, unless you spent your whole career studying these, and well, that's rather sad. Anyway, so as long as you can use the tool for what it should be used for generating basic structural information about functional groups present in a molecule, you'll be fine. Couple this with mass spectrometry data, and you have quite a bit of information about your molecule right there. The one thing IR is no good for is telling you anything about the molecular weight of the molecule. That's just no good. There's also no use about whether there's a ring or a straight carbon chain. It's again, unless you're really good at it, you'll be spinning your wheels. Anyway, let's just go back here. We'd said before that different functional groups absorb in different places, and they absorb to different degrees. Some absorb very strongly, so the percent transmission goes almost down to 0. Some absorb in a less strong fashion, and some only absorb in a very weak fashion. But one of the things that I'll talk to you guys about today are some characteristic peaks that you want to be looking out for, right, that will usually be of particular use for you. And there's always going to be CH groups in a molecule. You really can't get away from those. Knowing double bonds is particularly useful. Triple bonds exist in a very unique place, all off by themselves. Those are nitriles in the infrared spectrum. Alcohols, whether those OH groups are in an alcohol or in a carboxylic acid, notice the absorption of the OH group in an alcohol is different to the absorption of an OH group in a carboxylic acid. and that tells you something. Arene in a benzene ring. There are always a characteristic group of weak peaks between 1660 and 2000, usually a set of 3 or 4 little humps, telling you there is a benzene ring there. Carbonyls as well, this one's particularly important. Carbonyl group is one of the most identifiable peaks in the entire spectrum because it's kind of off by itself and it's really, really strong. Usually, down close to 0. Not always, but usually. Now, one thing to make sure that you... Oh crap, what have I done? Bollocks. Alright, there we go. One thing to understand about this table, it should not be taken as gospel. Alright? Not gospel. In class, I'll be giving you guys some, at least one handout that's way more detailed than this. Because carbonyl groups differ in terms of where they absorb depending on the functional group, whether it's an aldehyde or a ketone or an ester or an acid chloride. This list is a very basic list. So do not look at this list and say, well, how come things don't match up specifically with this? Well, like I said, this is not gospel. This is very basic. You should only use it as a super basic guide. All right? Okay, that's that out of the way. Let's take a look at a couple. Now, if I was to tell you that this was the infrared spectrum for ethanol, you wouldn't know. Well, you know now because I've told you. But I wouldn't expect you to know. The only thing I'd expect you to be able to take from this would be, well, I know that ethanol looks like this. The only functional group of any real note here is the OH group. Yeah, there are some carbon-hydrogen bonds going on in there as well. But let's see if we can spot where the OH group appears. Well, we just go back to here. In an alcohol, OH groups appear usually between 34 and 3650 wave numbers. The intensity is usually strong and broad. Usually, not always, but usually. Now, notice we have this strong and broad absorbance here. It actually starts, I don't know, probably just over 3000 and goes all the way to whatever that is, like 3700 or something. So already we have an absorption that doesn't exactly fit this, but it's in a general area. And notice there's nothing else that this could possibly be due to that's strong and broad, like so. So this tells you you have an OH group. These guys right here, these little set of peaks below 3000, the only thing they tell you is that you have carbon-hydrogen stretches. Anytime you have those sorts of stretches just below 3000, it tells you you have CH. And you have CH in pretty much every molecule. So you'll see peaks like this all the time. Okay. Let me close this. All right. Like I said, the main thing about IR is to tell you the difference or to do some useful characterization about functional groups. And to illustrate that, we have hexane, one hexene, and one hexine. Notice that just in a basic sense, the 3 spectra are different. But there's one thing that they all share in common. They all have this big, broad thing right here. All right. Now, they don't all look the same, but they all have this, and that's because they all contain CH groups. But there are differences. All right. Just take a look at what we have to the left of each of those groups. In hexane, there is nothing to the left of the CH groups, but in hexene, there is a sharp peak here that clearly isn't present in hexane. And then in hexine, there's a very sharp strong peak here that's clearly not present in either of those. All right, these are carbon-hydrogen stretches, and so we move to the left as our hybridization changes. So once we have our table with us back here, having access to this, and you would have access to this on a quiz or on an exam, having access to this is very useful. All right, and there's also the fact that here we just have carbon-carbon bonds. All right, here we have a carbon-carbon double bond. Here we have a carbon-carbon triple bond. Again, you would know these by looking at the corresponding table. But the point is, you can tell the differences here by looking at the functional groups. And notice, we didn't analyze 90% of all these peaks. In fact, we're not really bothered about those. The main ones that we're bothered about are the ones that we've circled. Okay? So, take-home point about an infrared spectroscopy is you don't want to be analyzing everything. Unless you want a headache, anyway. Alright. So, last thing here. Let's just take a look. The kind of question that you might see is, well, what functional group or groups, plural, do I have in this molecule? And so what you want to do is you want to go back to your table and say, well, okay, I don't know anything, but let's see what looks to be characteristic. For one thing, if there's anything strong below or above 1500, which this is, then you want to make sure that you make a note of it, because that's probably going to be something. And then anything that's 3000 or above, you want to make a note of too, because that's probably important as well. And also notice that, you remember we said virtually every molecule contains the big set of CH stretches just below 3000. Well, notice we don't have that here. We have some stretches above 3000, so that tells us something special about this molecule. It tells us there's probably no CH, or at least no aliphatic CH. Aliphatic means not aromatic. So let's see what we can do here. This big peak here, this is around, what is that, 15, 16, 17, 18, that's about, what is that, 17, maybe 1730 reciprocal centimeters, and that's strong. And if we go back here, 1730, strong, well, that fits right in there for a carbonyl group. We don't know what sort of carbonyl group, but we know there's a carbonyl group there. And what can we see for something that's kind of medium above 3000? All right, medium above 3000. Well, when we go here above 3000, well, that would be too strong and broad. Above 3000, that's too far above 3000. No, above 3000, okay. And then above 3000 too. All right. So what we have is we have a situation where we could have alkene double bonds, or maybe aromatic double bonds. And the way that we can tell which we have is we can just take a look at, see if we have any sets of peaks that I mentioned before, and a little grouping that correspond to whether we have an aromatic ring or not. So let's see. And we actually have a little group of the guys right here. So what this probably means is that C stretching is due to an aromatic ring. But bear in mind, when we looked at these numbers and these numbers are very similar. These numbers and these numbers are also very similar. So it's certainly possible to not necessarily get yourself confused, but give you several different options about what could be the case. All right. So what we have is a carbonyl. We have double bonds or possibly an aromatic ring. And those peaks just above 3000, probably either these alkene CHs or aromatic CHs. Okay. The only thing that we can't see from this table, and again this is why having something more comprehensive is useful, is that this group is actually a very small peak associated with a CH on a carbonyl group. Again, our table doesn't show that, but I'll be giving you something in class that does illustrate this more clearly, or in more detail at least. So, and you know what functional group that is, that's an aldehyde. So we've been able to generate a bunch of information from here, and that is the basics of infrared spectroscopy. This video has already been long already, so I'm just going to say bye-bye.